Hello. In this video, we're going to look at expanding binomials. Now to start with, we'll do a very simple binomial. We have x plus 1 to the power of 2. We can expand this with a little bit of FOIL. X plus 1 to the power of 2 means x plus 1 times x plus 1. First, outside, inside, last gives us the following terms. Combine the two middle terms to give you x squared plus 2x plus 1. All right, not a big deal. Let's try the next one. What if we had to expand x plus 1 to the power of 3? Now, this is a little trickier because we're going to have three terms, and we can't just FOIL them like before. You're going to have to look at the first two terms on their own. Now, this gives us x squared plus 2x plus 1. And then you have to expand that out with the last term. So one way to do this is to take the x squared into both of these. That'll be x to the 3 plus x squared. Then take the 2x into both of these. That'll be 2x squared plus 2x. Finally, take the 1 into both of these. X plus 1. Then we combine everything to give us x cubed. 3x squared, 3x plus 1. All right, let's take it up another notch. X plus 1 to the power of 4. Please pause the video and give this a try. Go ahead and expand all of the terms. All right, assuming you gave it a try, we're going to have x plus 1 times x plus 1 times x plus 1 times x plus 1. Now, if you wanted to, you could cheat a little bit. We know these three already multiply to give us x to the 3, 3x squared, 3x plus 1. We know that from the last example. So we can get away with just doing one more expansion, but I mean, it's still a lot here. We have to take the x to the 3 into both of these. We have to take the 3x squared into both of these. We have to take the 3x into both of these, and we have to take the 1 into both of these. So let's start with that top there. We'd have x to the 4 plus x cubed, 3x to the 3 plus 3x squared, 3x squared plus 3x, x plus 1. All right, now again, if you notice, these two terms group, these group, these group. So you get x to the 4, 4x cubed, 6x squared, 4x plus 1. And that would be our final expanded binomial. Well, the fun thing with this game is we can play it all day long. Let's do x plus 1 to the power of 5. So that means you'd have an x plus 1, an x plus 1, another x plus 1, another x plus 1, and another x plus 1. Now, you could either do these one at a time. I mean, we do know from the last example, at least we can shortcut the beginning part. So this is x to the 4, 4x cubed, 6x squared, 4x plus 1. But now we have to multiply each one of these terms into the x plus 1. And I mean, at some point, you just start to feel exhausted. And you're like, is there a faster way of doing this? Well, we're going to expand this one old school, and then we'll see if there's a faster way. So we get x to the 5, x to the 4, 4x to the 4, 4x to the 3, 6x to the 3, 6x to the 2, 4x squared, 4x, x plus 1. Now again, we group these terms, these terms, these terms, these terms. X to the 5, 5x to the 4, 10x to the 3, 10x to the 2, 5x plus 1. And at some point, you should notice that we have an interesting pattern going on. If you remember from our first example, the first example we had was 1x squared plus 2x plus 1. Then we had 1x cubed plus 3x squared plus 3x plus 1. Here we had 1x to the 4, 4x cubed, 6, 4, 1. Here we have 1, 5, 10, 10, 5, 1. Yes, if you haven't seen it already, this is indeed Pascal's triangle. If we start drawing out this triangle where we add numbers, for example here, 3 plus 3 adds to 6. If we add numbers to get the numbers below and put ones on the outsides, 1, 5, 10, 10, 5, 1, these numbers give you these numbers. Again, if I highlight them for you here, the 1 here is the 1 here. The 5, the 5, the 10, the 10, the 10, the 10, the 5, and the 1, the 1. It's almost like we could grab our triangle and just put x's right in here, and we'd be good to go. Here we'd start with an x to the 5 because it's the power 5 out here. And then we go x to the 5, and we count down x to the 4, x to the 3, x to the 2, x to the 1, and then no x. We could simply take the row with the numbers, take our x's and count down the powers, and we'd have our expansion in just a moment. No crazy foiling, no combining like terms, just a nice, wonderful shortcut. And indeed, that shortcut is fantastic. If you wanted, you could go ahead and do a quick example. So let's say we had x plus 1 to the power of 6. Well, you should be able to expand that. It's going to be x to the 6, x to the 5, x to the 4, x to the 3, x to the 2, x, and then a constant term. And we need some numbers in front of all these x's. Well, again, we had 1, 5, 10, 10, 5, 1. The next row will be 1, 6, 15, 20, 15, 6, and 1. So we just take each one of these numbers and plop it in. 1, 6, 15, 20. Let me just move that addition sign there. 15, 6, and 1. But unfortunately, this shortcut isn't going to work on everything, at least not the way we have it right now, because all of the examples we have were x plus 1. And here's where I'm going to throw a wrench into it. What if you have to expand x plus 2 to the power of 3? Go ahead and pause the video and give it a try. All right, assuming you gave it a try either with some kind of shortcut or with expanding, we do need to at least expand it so we know that our answer is correct. We can only check a shortcut if we have the long cut as well. And so let's go ahead and expand this out so we know what the answer should be. Those first two ones are going to be x squared plus 4x plus 4. And then we'll expand it here. X to the 3 plus 2x squared. 4x squared plus 8x. 4x plus 8. Let's group those terms. X to the 3, 6x squared, 12x plus 8. I mean, if we think about that Pascal triangle, we thought it was going to be this row right here. We thought the numbers would be 1, 3, 3, 1, but the numbers are 1, and let me just put that 1 in front here, an invisible 1. The numbers are actually 1, 6, 12, and 8. I mean, those aren't really the numbers from Pascal's triangle. How could we connect these to these? And it has something to do with the number 2. Now, again, I encourage you to pause the video and see if you can modify these numbers to make them become these numbers. All right, let me show you what I came up with. We're going to start with the Pascal numbers because they are good numbers. But now, if you notice, to get the 6, we're going to multiply it by 2. That's going to give us a 6. But if I multiply the 3 by 2, that doesn't give 12. Let's multiply that by 2 squared. Oh, well that works pretty good. 2 squared is 4. 3 times 4 is 12. And I'm going to multiply by 2 cubed. 2 cubed times 1 is 8. Oh, okay, so then if this was just 2 to the 0, That'll be still 1. And what you notice here is I have powers of 2, and in this case they're counting up. Now these are the Pascal numbers. And really I should have a row above that that has the x's, x to the 3, x to the 2, x to the 1, and x to the 0. These are the powers of x. And if you notice, the powers of x's are counting down. The powers of 2's are counting up. The Pascal numbers are kind of sandwiched in between. And then when you multiply the whole thing, you end up with 1x to the 3, 6x to the 2, 12x to the 1, and 8 as a constant. And that seems to be my answer. If I was to ignore everything, up here, and just focus on this, I didn't do any kind of FOIL or expansion or grouping like terms, but I was still able to get the final answer. So let's give that another try. Let's consider x plus 2 to the power of 4. See if you can use the shortcut with Pascal's triangle and those powers of x's and powers of 2's to just jump to the answer right away. And then we'll check it with expansion. All right, so assuming you gave that a try, we had 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So the answer should include these numbers, 1, 4, 6, 4, and 1. I'm going to put the powers of x here, x to the 4, x to the 3, x to the 2, x to the 1, and x to the 0. Then I'm going to put the powers of 2 here, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. So this would all work out to x to the 4. This will be 8x to the 3. This will be 24x to the 2. This is 8 times 4, so 32x, and then 16. So we should have x to the 4 plus 8x to the 3 plus 24x squared plus 32x plus 16. And to check this, we're going to actually use Wolfram alpha to allow us to expand the polynomial and see if we get the same answer. All right, great news. When we type in expand x plus 2 to the power of 4, the computer recognizes our input and gives us x to the 4 plus 8x cubed plus 24x squared plus 32x plus 16. So our shortcut gave us the same thing as the computer doing the algebra. And so, yeah, I think we're good to go. All right, so let's try x plus 2 to the power of 5. Go ahead and pause the video and give it a try. All right, so you should have the following. Again, we quickly draw out the Pascal triangle to give us our starting numbers. So we have 1, 5, 10, 10, 5, 1. We get those x to the 5, x to the 4, x to the 3, x to the 2, x to the 1, x to the 0. Remember, we're starting with an x to the power of 5 because we have a power 5 on our overall binomial. Then we're going to be counting up with the 2's. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. Now when we work that out, we get x to the 5 plus 10x to the 4 plus 40x to the 3 plus 80x to the 2 plus, what is this one, 16 times 5, another 80x, and then 32. All right, again, let's check our answer with Wolfram just to compare. All right, again, we can see the expand x plus 2 to the power of 5 gives us x to the 5, 10x to the 4, 40x to the 3, 80x to the 2, 80x plus 32. There's 6 terms total, and they're exactly what we got with our shortcut. So again, we should be feeling pretty good. Let's look at another example. Ooh, this one adds a bit of a twist. We have 2x plus 3 to the 5. Now, with this example, the 3 is different from a 2, so we probably would expect powers of 3. The 5 is still the same, so we should look for that Pascal triangle row with the number 5 in it, with the 6 terms. But the 2x is different from an x. And I think that's going to change your expansion. So I'd encourage you to pause the video, give it a try, at least come up with an attempt for the shortcut, and then we'll see if you got it right or if there's some tweaks that need to be made. All right, so assuming you gave that a try, again, the numbers are 1, 5, 10, 10, 5, and 1. And we're going to have those powers of 3 counting up, 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, and 3 to the 5. And we do have our x's counting down, x to the 5, x to the 4. Let me do that in another color. X to the 5, x to the 4, x to the 3, x to the 2, x to the 1, and x to the 0. But it's not actually just an x, it's a 2x. So the whole 2x needs to count down. And this is very important. The 2x is all raised to the power of 5. The 2x is all raised to the power of 4 or 3 or 2 or 1. So what that means really is this is going to give us, for example, an extra 2 to the power of 5 next to our x to the 5. So this is going to definitely change that number in front. If you thought the number in front was just going to be an x to the 5, or even just a 2x to the 5, that's incorrect. It's 2 to the power of 5, which is 32 x to the 5. All right, the next term has a 2 to the power of 4, and an x to the 4, and a 5, and a 3 to the 1. So the numbers here we have are 2 to the 4 times 5 times 3 to the 1. And that's all going to go together to give you 2 times 2 times 2 times 2, 2 to the 4, times 5 times 3, which is 240. Now, if you made a small mistake but you want to fix it, go ahead and pause the video and fix up your coefficients. All right, let's keep going. Here we'd have 2 to the 3 times 10 times 3 to the 2, 720x to the 3. Now we have 2 to the 2 times 10 times 3 to the 3. It's going to be 1080x to the 2. 2 to the 1 times 5 times 3 to the 4. That's 810. And then finally, 2 to the 0 will just be 1. So it's 1 times 1 times 3 to the 5, which is 243. Now again, let's go ahead and check this on Wolfram to make sure that our shortcut is legit. All right, there's our expansion, and we can see that 32x to the 5 in front, 240, 720, 1080, 810, 243. All right, so I think we finally have our full shortcut that includes all the changes. When you change the number here, when you change the number here, even when you change the number here, I think we're good to go. So let's look at one final example. Go ahead and expand 3x plus 4 to the power of 3. Go ahead and pause the video and give that a try. All right, so you should have the following. We make the Pascal triangle. 1, 3, 3, 1. Now the powers of 4 are going to count up. 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3. Powers of 3x are going to count down. 3x to the 3, 3x to the 2, 3x to the 1, 3x to the 0. And then we're going to get each term. So the first one will be 27x to the 3 plus 108x to the 2 plus 144x plus 64. All right, let's go ahead and take some notes on this. The shortcut we've been doing has a fancy name. It is called the binomial theorem. And the binomial theorem is a method for, you can think of it as a shortcut or a formula, so it's a shortcut. Slash, you can think of it as a formula or a method for quickly expanding something that looks like this. AX plus B to the power of n. So anytime you have some kind of binomial, I mean, really it doesn't even have to be AX. You could just even write it as A plus B to the power of n. And the way you do this, the way you expand it is, well, just like we had. You use the row from Pascal's triangle. The powers of the A count down, the powers of the B count up, and you're good to go. So here we might want to write that down rather than doing a full example. It might be a little bit nicer to have some things written down. So let's write down 5x plus 2 to the power of 4. So what we need to know here is that for the 4, this means we're going to use the 1, 4, 6, 4, 1 row, the row that has the 4 in it. For the 5x, it means we're going to have 5x to the 4, 5x to the 3, 5x to the 2. So these are counting down. Count down. Then for the 2, we're going to have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. These are counting up. And then in the end, you have to combine everything. So maybe I'll just put it down here so we can see our final row with all the information. We have our 1, our 4, our 6, our 4, and 1. We have our 5 to the 4, x to the 4, 5 to the 3, x to the 3, 5 to the 2, x to the 2, 5 to the 1, x to the 1, 5 to the 0, x to the 0. Down here we have our 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. And then underneath each one of these is going to be our term. So let's just crunch those out. 625x to the 4 plus 1000x to the 3 plus 600x to the 2 plus 160x plus 16. Now, a few things to remember. I mean, there's a lot to remember on the binomial theorem, but if you have a plus b to the 4, that's always going to give you 5 terms, right? It's always one more than the power, So that's something to keep in mind. Here we had to the power 4, and we got 1, 2, 3, 4, 5. And you might want to write down something for yourself in terms of a negative. We didn't have any negatives here, but you could put a negative here, and that would just get absorbed into that second term. So the second term would have a bracket around it with a negative. You'll definitely see some of those on the worksheet. So for practice, you can try worksheet 11 and 11.5. All right, hopefully you enjoyed this video, and as always, thanks for watching.